Hi everyone. In this video, as part of Manuary, I'm going to be discussing the fundamental particles of matter. One of my previous videos, we discussed the model of the atom, which we now understand is made up of a small positively charged nucleus, which itself is made up of protons and neutrons, with electrons orbiting around the outside. We now understand that actually the protons and neutrons inside the nucleus, though held together by the strong interaction inside the nucleus, are actually themselves made of smaller fundamental particles called quarks. And when I say fundamental here, I'm referring to particles we don't think we can break up any further. Electrons are, however, fundamental particles, and they're an example of a type of fundamental particle called a lepton, which doesn't feel the strong interaction, which protons and neutrons do, but does feel the weak interaction, which is responsible for certain types of nuclear decay. And also because it's charged, it feels the electromagnetic force too. There's another type of lepton called a neutrino, which is neutral and actually doesn't even feel the electromagnetic force, so it only undergoes weak interactions. This is something you've already studied, and now's a great time to pause and I write down everything you can remember so you can check it off as we go through, and otherwise I'll get started on the whiteboard. So as I implied in my introduction, we can classify fundamental particles into two types. One is the quarks, and one are the leptons. So as I mentioned before, quarks feel a force called the strong interaction. So they feel the strong interaction, whereas leptons don't. So quarks feel the strong interaction and they feel the weak and the electromagnetic forces. Whereas leptons only feel the weak and the electromagnetic force. And of course, they only feel the electromagnetic force if they're charged. On the right-hand side, I'll just quickly remind us all of what we think the four fundamental forces of nature are. So we've got gravity, which is probably the one you've heard of most, but I'm actually going to put it in brackets here because actually when you look at particles on the smallest scale, actually gravity is the weakest of the four forces, and we can describe most of the behavior of fundamental particles without worrying about gravity at all. In fact, we can describe all of it. So then there's the strong interaction, which binds the protons and neutrons inside the nucleus, and also, as we'll come to see, explains how the quarks are bound together inside bound states called hadrons, which include the neutrons and the protons. There's the weak interaction, which is responsible for processes like radioactivity. And then there's the electromagnetic force. And as I implied, when we're looking at fundamental particles, actually we can describe their behavior just by considering these three. It's a bit of an outstanding mystery about why gravity is so much weaker than the other three forces on this scale. It's also very interesting, actually, how we have to model fundamental forces on subatomic scales. So when discussing gravity, we've often referred to the concept of a gravitational field. So an object with a mass generates gives rise to a gravitational field around it, and particles feel what we call a non-contact force when they move in the gravitational field of a more massive object. However, when we move to the quantum realm and start considering fundamental particles, we have to actually consider forces as behaving very differently. And in particular, we view particles as being caused by the exchange of particles that we refer to as gauge bosons. And if this is all a little bit bizarre to you, please don't worry. Those of you that go on and study particle physics further will have lots more opportunities to think about this. So I'm just going to draw an arrow in my box on the right-hand side to note that we understand that the three forces that we're worried about here, so the strong, the weak, and the electromagnetic interaction, are mediated by the exchange of what we call gauge bosons. And one way to think about this would be if we were standing in a room and I were to throw a ball at you, in catching that ball, you might feel the force pushing you backwards, and that's how we would exchange a force. Of course, it's easier to visualize in the case of repulsion. However, when thinking about attraction, you probably have to think of some kind of boomerang being thrown, such that the force you feel is such as to bring you closer to the person throwing the boomerang. And actually, it's a particular property of the gluon, which is the exchange particle for the strong interaction, that causes an interesting property, which we actually refer to as confinement, which means that you can actually never see a quark on its own. So they always must be bound in states called hadrons. If you were to try and move two quarks apart, then actually what would happen is as you try and move them apart, the energy stored in what we can think of as the force field generated by the gluons increases, such that eventually this energy will be enough to generate new particles, and these are generated in the form of a quark and an antiquark pair. I'll be talking about antiparticles soon. But yeah, it's an interesting observation of the strong force that you can never see a single quark on its own. And that's one of the reasons why it took scientists a long time to develop the model of matter that includes quarks, because we can't actually directly observe them. Okay, so let's go back to our quarks and our leptons for now. So I just mentioned that actually quarks can't be observed on their own, and actually they're always bound into states called hadrons. For example, the proton and the neutron are examples of hadrons. So for now, I'll just talk about the lightest two quarks. So we've got the up quark and the down quark. So the up quark has a charge of plus 2/3. And the down quark has a charge of minus 1/3 in relative charge. So this means that a proton, if you just try and conserve the charges, So these are, of course, in units of the elementary electric charge. So a proton is up, up, down, and a neutron is down, down, up. Quarks, well, these two quarks, at least the up and the down quark, are very light particles, but actually measuring their masses also was a challenge because, as I said before, you can't see a quark on its own. So now let's go over to the leptons. So as I said, these only feel the weak and interaction and also the electromagnetic force if they're charged. So the electron is an example of a lepton, and that has a charge of -e. And the other lepton you need to know about is a neutrino. And as its name suggests, it's a neutral particle, so it only feels the weak interaction. It's important to realise that in all interactions that you have to consider involving particles, a quantity called lepton number is conserved. And specifically, L is 1 for the electron and the neutrino, and I'll be coming on to antimatter in just a minute, and you have to assign L is -1 for antineutrinos and positrons, which is the anti-electron. So if you ever have an interaction and you write down the lepton number for the left-hand side, it must also balance on the right-hand side. And in particular, if you assign a lepton number of 0 for your any process involving your hadrons or quarks, then if you have a hadron decaying via, say, the weak interaction, then you always have to produce a lepton in an anti-lepton because the total lepton number must be 0. Okay, so I've mentioned them a few times already, but it's important to note that all of the matter particles I've mentioned so far, so the quarks and the leptons, also have a corresponding antiparticle. And the antiparticle has the same mass, but opposite charge. There we go, opposite charge. And antiparticles are actually very interesting because they were predicted by a scientist called Paul Dirac when he was trying to write down a quantum equation to describe the electron. So it turned out that the maths didn't make sense unless there was another so-called anti-electron or a positron that had the same mass but opposite charge. So this was predicted by Paul Dirac and later observed in an experiment by a scientist called Anderson. And this was a very nice example of a scientific process whereby particles were actually predicted and then could be go away and searched for experimentally. So, for example, we can consider positrons as the anti-electron and also antineutrinos, but quarks also have antiparticles. So we have, you know, if I call my up U and my down D, you can consider an anti-up, which has a charge of -2/3 times E, and an anti-down, which has a charge of +1/3 E. And antiparticles are often also important when trying to balance equations for reactions between particles. So in my previous video about the structure of the nucleus, I mentioned that actually, although neutrons can be stable when bound inside the nucleus of an atom, actually neutrons in a free neutron, so when it's not bound, actually would decay relatively quickly with a half-life of around 15 minutes. So the proton is actually the only stable hadron, so the bound state of quarks. And actually the neutron decays into a proton plus an electron plus an antineutrino. And we can now understand why we need this antineutrino in terms of lepton number. So the neutron has a lepton number of 0, the proton has a lepton number of 0, the electron has a lepton number of 1, and the antineutrino has a lepton number of -1. So I think I've just about run out of space for now, but one last thing I'll say about particles and antiparticles is that if by Einstein's equation E is equal to mc squared, you can often get a pair production of a particle antiparticle pair. There we go. So, for example, we could have a photon, which is the particle responsible for the electromagnetic force, and that could convert into an electron and a positron. And again, this process is okay, it still conserves the lepton number. And often this process has to occur near a nucleus or some other particle in order to make sure momentum is conserved overall. Unfortunately, I really have now run out of space to write notes on, so I'm going to stop this video. I hope you found it interesting. Some of this probably goes a little further than what you need to know as at A-level, so do check your curriculum as you're going through it. And please email if you have any further questions. In the meantime, it's been nice speaking to you all, and I hope to see you soon.